go. Here we go, here we go. Week 13, your homework. What problem was that you discovered? Here, someone, or Lawrence discovered, what was that? Hang on, I gotta bring this up. That in this picture I posted with your homework problems, that one of these problems, for some reason on my book that I got these pictures, took these screenshots from, is different than his book. That one of the problems are different. So I want to bring it to your attention. Do you remember which one it is, Mark?
I think it was 15A.
15A, so let me jump down. And mine says, you got your book open on it?
Yeah, it says minus 2.7x squared.
Okay, but it's minus, right?
Yeah.
Okay, look at your book. If you're using your own book, you might have a minus here where it says 15 minus 2.7x2 right there. And this problem here says plus. I think the answer that I'm sending to the grader to grade this with is going to use the plus. So try to use the plus. Use this picture instead of your book. How's that? Does that help? Has everybody got it? So that at least it's consistent then with the answer? But that's the only inconsistency you found, right? Is that this, for some reason, this is different in my book than yours. And his is a 4th edition, and this is a 4th edition, so it doesn't even make sense that we'd have two different problems. So it's kind of weird. I don't know, I think mine might be the international version maybe, and that's why it's different, because I noticed that with some other problems that the international version has a couple of changes that are not in the regular version. Maybe that's why, I'm not sure. So there's that announcement. So there's that homework. Anybody finish these problems? So I have at least 5 people have handed in. How long did it take you to do all these problems, would you say? 10 minutes. 10 minutes, okay. There we go. Now the other part of your homework is right here, where you're supposed to use data analysis, pick regression, and then you're supposed to put your table right here on the spreadsheet. They use the cell locations of the information off the table to do these, how many forecasts? 4 forecasts here. When X is 20, when X is 21, when X is 22, when X is 23, which stands for the month number. And get your forecast here using cell locations. Everybody understand what's expected there, right? But now, here it is, goodness of fit. We're using this linear regression to do forecasting, but there's going to be these other forecasting techniques you're going to learn in the other classes. And if we learn anything on next week, it might be another forecasting technique. But let's pretend we've learned multiple ones. But at this point, we've only learned linear regression forecasting. But there's all kinds of different forecasting techniques out there. And these are the 3 different calculations that exist, among some others, where you can evaluate which particular forecasting model works with the data the best, and then you should select that one to do your forecast for a short period of time. 3 months, 6 months, it depends on, it's like what your periods are. If each period's a month, you might go 6 months. If each period's a year, you might go 2 years. And then you reevaluate using these calculations right here to determine if forecasting technique works best with the data again. Sometimes a different forecasting technique all of a sudden starts working with the data better because there's been some kind of change in the economy or something, and so your data's kind of been changing. Anyway, these are the 3. Now real quick, coefficient of determination is also referred to as R squared. That's that second one, called coefficient of determination. And this is how it's calculated. SSR over SST, simplified. There it is, simplified. All right. The adjusted R squared happens to also be called the coefficient of determination adjusted. All right. And the top one is called the standard error of the estimate, which is right here. If we were manually calculating, it'd be SSE, which will make sense in a minute, SSE over the sample size minus the number of explanatory variables, I'll explain that in a minute, minus 1, the whole thing square rooted. That's that top one. Now, when would you use standard error of estimate? When would you use the coefficient of determination R squared? Or when would you use the adjusted? It's all about how many explanatory variables are being used in the forecast technique. For example, if linear programming is involved, let me take a look here. Hang on. See these 2 forecasting models right here? 1 and 2. I'm going to see if I can make this bigger. There they are. See these 2? Y is the forecast equals that B sub 0 is the intercept. B sub 1 times x1, slope times whatever x1 is. The other model's using the slope times x2, a different x2, a different x is all, a different slope maybe, or the same slope. The question, what I want to explain to you is that when you see an equation that does forecasting, the x's are the explanatory variables. Did everybody hear that? The x's. So you count how many explanatory variables by how many x's if all you have is the equation. You may have a story that says, hey, we're comparing two forecasting models, and the first one has 2 explanatory variables, and the second one has 1 explanatory variable. It may be in words, or it may be in an equation like this. But if it's in an equation, you just count the x's. So if you notice, both model 1 and both model 2, both have only 1 explanatory variable. When they have the same amount, both have 1, or they both have 2, or they both have 3. When they have the same amount, you are to use, let me go back to the PowerPoint, number 1 or number 2. Either the standard error of the estimate or the coefficient determination R squared. That's when the number of explanatory variables are the same for each model, forecasting model being compared. If each forecasting model being compared has the same number of x's or explanatory variables, we're using 1 or 2. And how do you decide 1 or 2? Whichever one is making it more clear that which model's the best one for your data. Okay, now let me make sure you've got this written down. If you go, oh, these 2 models have the same number of explanatory variables, right? I'm going to use maybe standard error of the estimate, or I'm going to use R squared, coefficient of determination. And you're looking at it and you're going, okay, you ready? When you look at standard error of the estimate, you want to pick the model that has the lowest standard error of the estimate. Let me repeat that. The model that has the lowest standard error of the estimate is the better fit model, and the one you would like to use in the future to do your forecast with. Everybody hear that? But here's the weird part. Number 2, coefficient determination R squared, is whichever model has the highest number when you're using coefficient R squared of determination. Whichever one has the largest number. Now be careful. You may say, okay, I'm going to use R squared, coefficient determination, because these 2 models have the same number of explanatory variables. But you notice that one is higher than the other. One model has a little larger coefficient determination, but they're really close to each other. They're so close that you go, well, maybe I should use instead standard error of the estimate. And that's what I want you to figure out, is to say, whichever one makes it more clear as to which model fits better. That's the one you want to use. Did everybody hear that? 1 or 2, you're going to use one of those 2 because the 2 models have the same number of explanatory variables. And you're trying to decide which one to use, whichever one is more clear, telling you which model is better. Whichever one is more clear. If the 2 numbers, you're using, let's say, standard error of the estimate, and the 2 results are darn close to each other, well then jump down to coefficient determination R squared, because maybe those numbers are a lot farther apart and are making it more clear as to which model fits better. Now, let's say the 2 models, I heard a question coming in, hang on. Let's say the 2 models have a different number of explanatory variables. Maybe model 1 has 1x, model 2 has 2 x's. We're using an adjusted R square then. The adjusted coefficient determination R square is the one you use if the models you're comparing have different numbers of explanatory variables, different numbers of x's, which, by the way, I found an example. Let me jump down here to the next problem. That was 46 that had the same amount. Now look at 47. See the 2 models, model 1 and model 2? Each of them are forecast equals the intercepts, but look at how model 2 has 2 x's, where model 1 only has 1 x. They have different number of explanatory variables. The way to evaluate these 2 models is to only use the adjusted R squared coefficient determination. Do not use standard error, do not use R squared coefficient. It's the adjusted R squared you would use, adjusted, because they have different numbers. Everybody get that part? So you're not going to have a problem on the following exam trying to determine what I'm looking for in an answer when I'm asking you to compare these 2 models. If you notice these two models have different numbers of explanatory variables, you know which one to use. And if they have the same explanatory variables, then you've got to figure out which one to use based on which one is making it more definite. Now, here's some examples. All right, let me jump to this one here. First of all, let me go back up, there we go. This is number 46. Look at the two models at the top. Look at the answers. Oh, wait, you can't even see part of the answer. Oh, what happened? Do I have to go up here? Where's 46? Oh, this is right out of the book. I thought maybe I had a picture. I know you can't, let me see, r squared. See how it's kind of off? The top numbers are r squared. The middle numbers are adjusted r squared, and the bottom ones are your standard error, okay? The SE stands for standard error. So now, my question for you, looking at the two models, and I want, think about it closely now, take your time. Should we be using r squared, adjusted r squared, or standard error at the bottom there? Which one should we use? Let me find the answer before you tell me. Okay, all right, we're there. Let me look at those. Let me look at those. Oh, I've got a clear answer. What's your answer? What?
R2 or SE.
She's saying either R2 or SE, but there's only one answer, but she's in the right direction. She's noticing that the two models have the same number of explanatory variables, so that's why we're either using SE or R squared. But are we using R squared or SE? That's the question. What? Which one? Wow, she's just mumbling. I thought she was giving us some. What? She's
Okay,
good.
No, I was just wondering, how did you figure out that they have the same?
Look at the two models at the top there, and look at how they have the same number of x's. See how both of them have the same number of x's? So that's how we know we got to use R squared or SE standard error. Go ahead.
When you said earlier, use the model with the lowest, is it lowest standard error?
No, use the model that makes it the most obvious as to which model's the best. When you realize, okay, these have the same number of explanatory variables, so now it's between SE and R squared, you pick the SE or the R squared that's the most clear as to which one's the better model. One of those two are making it more clear that one model's better than the other. Is it R squared or SE? SE. Why SE? Greater gap between the numbers. 104, I can't see it, 914 versus 101274. But look at R squared. 0.459 versus 0.496. They're kind of closer together. Do you notice how they're closer together than the other two? So we're going with SE. Now, which model? Are we going with model 1 or model 2? Model 2. Whichever one has the lowest SE. Now here's the bad news. Here's what's awful about this one. This could get confusing because if you went with R2, R squared, which model would you pick?
1.
No, it's still R2. It's rather, here's why. Because don't forget with R squared, it's whichever number is the largest. And with SE, it's whichever number is the smallest. And that's where it can get confusing. So be careful. All right. Yes?
So what is a large gap? Like how does
If you take like 104 minus 101, that's 3.0, but up at the top here, 0.459 to 0.496 is 0.0, I mean, it's not even a 0.5. They're not even 0.1 a difference between them, you know?
so when there's a bigger gap, how does that
Bigger gap, that means it's being more defined as to which is trying to tell you which model's better. Yeah.
I'm sorry, what are we looking for in the models again?
How many x's? Look at model 1, how many x's do you see?
Just one.
1. And model 2, how many x's?
Just one.
So since they're tied, they both have just 1, we know we gotta use either R squared or SE. We can't use adjusted.
So if there was more than one, then we would look.
If one of them had more than 1. If they could both have 2 x's, and we still gotta use SE or R squared. It's when they have different number of explanatory variables between the two models. Matter of fact, let's look at one right now. I'm giving it away that they have different numbers, but here we go. There we go. Here we go. Which one should we use? We use R squared, adjusted R squared, or SE? Adjusted. Why adjusted? The different number of x's. Model 2 has 2 x's. Model 1 has 1 x. X represents how many explanatory variables. Don't get me wrong. If this is a final exam question, I may not use the model like that. I may use words that say model 1 has 1 explanatory variable. Model 2 has 2 explanatory variables. Now and I'm not gonna say which goodness of fit, should you use, whatever. Instead, I'm gonna say, tell me which model's better and which numbers did you use. I'm letting you pick which one. And on this one, you're gonna use adjusted because they have different number of explanatory variables. Now, when you look at adjusted, you're gonna recommend model 1 or 2. Model 1, but look at how close they are. Do you see how close they are? They're almost tied. It's like either model would work here. They're so close. But for the answer to the question on the exam, you're right. You're gonna say model 1, I compared 0.748 to 0.747, and model 1 has the larger adjusted R squared, right? You didn't even have to give me the numbers if you say model 1 has the larger adjusted R squared. That tells me you're looking at the right numbers. As long as I can tell by your answer that you're looking at the right numbers, that you realize that these two models had different explanatory variables and it took you to the right road to go to. That's what I'm looking for here on the answers. All right, so there's where we're at. Now, how did we get here? How did we get to this counting how many explanatory variables and trying to figure out which one of these goodness of fit models will tell us which model's best? And here's the manual part of it right here. All right, here's how we got here. To find this coefficient determination, you got to find SSR or SST or SSE. Here's a key formula for you. Now, I want to prepare you for the final exam. I'm going to give you part of the information, and you got to use logic and algebra to come up with the rest of the information. And here's a key formula. I can tell you in advance, if I'm trying to use any of these particular variables, I only have to give you 2 of them. I don't have to give you all 3. As long as you have that formula, you can find the 3rd one, right? What? What does that look like? What do you mean? Seriously? I mean, let's pretend this is our unknown, and this is a 7, and that's a 2. Okay, what's that one? Oh my God, my grandma got that. Oh, we brought her up from the grave. 7 minus, we just subtract 2 on both sides, we get SSR all by itself. SSR equals 5, you get it? So you just use algebra to find the 3rd one. Now, once you have all 3 of these, you take SSR divided by SST, you just find your coefficient determination. Or let's say all you have is this data right here. How many pairs of data do we have? How many sets here or whatever? 3, there's 3 there. So this, look at this, if you have your SSE, because I gave you 2 of these, you could say, okay, whatever SSE is, I'm making up a number. What was it right now? Was it 2? 2, let's say, this is pretend, divided by sample size, you just told me 3, minus how many x's do we have among our variables here? How many we have a y, how many x's, rows or columns of x's do we have? 1. There's only 1 column of x there. We don't have x1 and x2. We don't have a second explanatory variable there. So how many explanatory variables? 1 minus 1. 3 minus 1 is 2, minus 1 is 1. So in this case, I'm not done yet. That'd be 2, and then we square root it. That's how we find our standard error. Standard error is just the SSE over how many pairs you have, or how many sample size you have, minus how many explanatory variables, minus 1. Now that was all hypothetical. I'm getting rid of this. How do we find, let's say I may only give you enough information to find 2 of these. And here's an example where, okay, here's x, here's y. Here's x minus the mean of x squared. We did this like last week, I think it was. It wasn't even Monday. I think we did it last week. I got all these here. Hang on, I'm going to do them kind of fast because this is all review from last week. This was x minus the mean of x squared, which is a 4, a 0, and a 4, which we added up to get an 8. And we used that number with this column here, which is which are x minus the mean of x times y minus the mean of y. This was 6, this was 0, this was 4, and that equaled 10. Then we took 10 divided by 8, which equals 1.25, and this is our slope. Is this all familiar? Remember how we got our slope last week with these numbers? And then Monday, at the beginning of that lecture, I said, hey, here's what we didn't do last week was SSE. I'm going to make sure to show you SSE. We took the forecasting formula. Remember, what was the intercept? Hang on, what was it? Oh, our intercept. here's the slope, the intercept was, this equals our, the mean of y minus the slope, 1.25. Notice I'm using minus because we're doing the intercept, not forecast, we're doing the intercept, minus times our x, whatever x is. We plugged in 6 for x, we plugged in 4 for x, we plugged in 2 for x, and let's get our forecast. Let's put our forecast right here. You know, this is what I don't have. And our forecast ended up being, what was the first one? Again? Oh yeah, 9.5. 9.5. Our second forecast was 7. Our third forecast was 4.5. There's the forecast once we had them in there. Now that we have, here's our actuals. Here's 10, 6, and 5 by putting 6, 4, and 2 in for x. Here's the forecast. If we were using our forecasting technique, had we put a 6 in, we would have got 9.5. Well, that's different from 10, so it's slightly off. We put a 4 in, we got 7. Well, it's different from 6, slightly off. We put a 2 in, we get 4.5. Well, that's different than 5, so it's slightly off. It's just a matter of, are these forecasting models, how much off are they? Whichever one is less off is the one we want to use to forecast the future. So now, we have our intercept, by the way, this ends up equaling 2. So here's our forecast formula. This is all review still. Forecast equals the intercept, which is 2. Now this time it's plus, not minus, because this is the forecast. 1.25 times x. And we plugged all those x's into that forecast formula and got those forecasts. Here's how you get SSE. This is what we talked about on Monday at the beginning of the lecture. We took each one of these y's, 10, 6, and 5, and subtracted the forecast that we got when we plugged these x's in. 10 minus 9.5 was, where am I? Y minus, oh, this is supposed to be squared. Sorry, my fault, this is supposed to be squared. There you go. Y minus the forecast, which is 10 minus 9.5 is 0.5 squared, so this equals 0.25. Then there's 6 minus 7, which is negative 1 squared equals 1. Then there's 5 minus 4.5, which is 0.5. We square that, and that equals 0.25. So we added those up, we got 1.5 as SSE. There's one of the numbers, SSE. Now, if we want to get SSR, here's the formula. Each forecast minus the mean of y squared. Let's do a couple so you can see how this is done. Each forecast, so here we go. Here's our forecast minus the mean of y, which is 7. So 9.5 minus 7, 2.5 squared. Someone got a calculator. I'll just put 2.5 squared here. 2.5 squared equals. Let's do the next one. Our forecast 7 minus the mean 7 equals 0 squared, which equals 0. Our last one, 4.5 minus 7, we're always using the mean, is negative negative 2.5, is that right? Negative 2.5 squared. Negative 2.5 squared. What's 2.5 squared, anybody? 6.25? 6.25 and 6.25. We add 6.25 plus 0 plus 6.25, 12.5 is SSR. SST, the last one, that will help. Once we have SSR and SSE, I don't have to do SST. Matter of fact, I can do it right here. Ready? SSE, which we just got at 1.5. SSR, which is 12.5, is that what that says? 12.5. What's our SST? You just add them up. 1.5 plus 12.5, 14. Let's make sure, though, that we're right. This is a good check and balance. If we manually do our SST, and it comes out to 14, we know we got it completely right. And once we have those numbers, we can manually get these numbers. But I'm not going to ask you on the final exam to manually calculate all these. Here, let me tell you what's probably going to happen, though, is I'm probably going to say, hey, you got a slope of 1.25, you got an intercept of 2. Your SSE is 1.5, your SSR is 12.5. forecast this number, do this, or tell me what the coefficient of determination would be, something like that. And the other part you need to be ready for is when you're given this output to compare models, and you're told how many explanatory variables are for each one, you're able to respond to me to tell me which one you use to compare the models and which model's best. You know, did you use R squared, which is the coefficient of determination, or did you use the adjusted R squared coefficient of determination, or did you use the standard error? What did you use, and which model's best? By looking at this output. Meanwhile, is this 14? This is each y minus the mean of y squared. Not the forecast, the actual y. 10 minus 7 squared. So this is 3 squared, which equals 9. This one is going to be 6 minus 7 squared. Negative 1 squared, which equals 1. This is going to be 5 minus 7 squared. 2 squared equals 4. 9 plus 1 plus 4, oh, 14. Look at that. Oh, I can't believe that worked. Negative 2 squared then. Okay. Same answer. Hang on. There. The whole point squaring is we're getting rid of the negatives.
How did you get the forecast for y? Like the 925 and the 7?
You ready? That was on Monday. Here's the forecasting one. We put in an x, multiplied times 1.25, and added 2 for each one of these. So here we go. Ready? And Lilia, let me show you. 6 is the first one. 6 times 1.25. Looks familiar?
Yep.
And then we put in 4 times 1.25, then we put in 2 to get those forecasts. So we took each actual explanatory variable and plugged it into to get our forecast to compare to actuals. Go ahead, Joe.
So for the standard error formula, how did you find how many explanatory variables?
I counted how many x's there were, like this. If I had raw data here, matter of fact, here we go. You tell me how many explanatory variables are in this example. Ready? Hang on. Where is it? That's not it. Hang on. There we go. How many explanatory variables are there in this example? We'll start at the top left. Let me make it bigger so you guys can see it. What is it at here? 100? Let me move it up. Okay. How many explanatory variables? How many x's are there? One column of x's. And there's not a second column of x's, or there'd be 2 explanatory variables. There's only 1, so you can kind of tell by looking at the raw data. Now look at what I did here. This is each one of these y's, 10 minus 7, 6 minus 7, 5 minus 7, squared. I add up the squares, and look at that, 14 SST, 14 SST. This is posted, everything we just did on the board being done through Excel to get these SSTs. Let me keep going now, ready? Here are the other columns. Here's the sum of that x minus the mean of x squared. There's that 8 right there. Here is this column, which is x minus the mean of x times y minus the mean of y. Right there, all added up, 10, so we got a 10. That's where this 1.25 slope comes from. 1.25 slope comes from. And you go here to the intercept. Here's the calculation for the intercept. D9 minus H13 times C9, which gives us a 2 for the intercept. Now, look at over here to the right, SSR. Forecast. I'm taking every one of these x's, 6, 4, and 2, and I'm plugging them into the forecast. H14 plus H13 times C5, and here's our forecast. 9.5, 7, and 4.5 in that column right there. Then I take each one of the forecasts and I subtract the mean of y, and then I square it. There they are, 6.25, 0, 6.25. And then I added that column up and I got 12.5 SSR. There it is right there. Now let's scroll down a little. We have our last column here. I took each y minus the forecast of y and squared it. Each y, minus the forecast of y and squared it. So there should be a 0.25 there, a 1 and a 0.25. You add them up, 1.5 right there. And so there's the SSE. So you have manually SST, SSR, and SSE all calculated on this spreadsheet that's posted. And then the formula SST equals SSR plus SSE, 14 equals 12.5, there's 12.5, plus 1.5, which is right there. Now, here we go, coefficient of determination, all right? before I click on it, at 0.89 right there above my pointer, I want you to look at the cell locations and tell me, here it is, coefficient determination, what is entered right there in that cell that does this right here to come up with that number. What cell locations? Let's see, SSR, where's it at? K18, that's right, K18 divided by, what is that, G9? Let's take a look. There it is, K17, it's not 18? Well, it looks like, oh no, 17 is where the number's at, 18 is where the letters are. K17 divided by G9, there's our coefficient of determination. Now let me show you something. You ready? Data analysis, regression. Yeah, I gotta find it. Regression. All right, let me get over here. Let me scroll up. Click labels. Where's our Y data? There it is right there. Y, there's the label plus the data. There it is. Where's the X data? Here's the label X plus the data. There you go. New worksheet. Here we go. Now, don't forget what's our, hang on, here we go. Let me go back to worksheet 1. Don't forget, what's our correlation of determination? You ready? We calculated 0.89286, let's say, 0.89. Look at the output from our regression model. Right there is our multiple, or where's our square? There's our square right there. Let me put a star by it right now. There's our squared, 0.892857. Having data analysis done, came up with the same thing. Now, let's go back to our spreadsheet. Standard error of the estimate. Standard error of the estimate is right here. SSE, so it's going to use the cell location where SSE is, divided by, and then I probably just put in 3 minus, and then I counted 1 minus 1, and then I square root it. Let's see if that's correct. Let's take a look. Here we go. Equals square root I-24, so that must be where SSE is, I-24. Where is it? There it is, I-24. Divided by 3 minus 1 minus 1, parentheses, parentheses. So I'm just doing this right here, and I get 1.2247. Let's look at see what Excel got. There is our, where is this? Our standard error, 1.22. Let me put it, star 1.2247. There it is, the same thing. 1.2247. Now our adjusted. This is the only formula I don't think I showed you because I thought there's no reason to even look at it manually. It's such a crazy formula. But here it is. I'm going to show it to you. Where is it? Hang on. Where is it? Adjusted. I went the wrong way. That's it. There it is. No, that's not it. Darn it. Hang on. There it is. You take the coefficient determination. That's what R squared is. You don't square it. R squared is the coefficient determination. You subtract it from 1. You multiply it by the sample size minus 1 over the sample size minus the number of explanatory variables minus 1. Think about that for a minute. 3 minus 1 is your denominator. 3 minus 1 is your numerator. Multiply that times 1 minus the coefficient determination. Then you take all of that, subtract it from 1. That's how you get your adjusted coefficient determination. No way I'm going to ask you to manually calculate that in any form or fashion, but I want you to see it. But look at how it is on this example. Here it is. It's 1 minus E22. There's our coefficient determination, 0.89, E22, times 3 minus 1 divided by 3 minus 1 minus 1. We get an adjusted coefficient determination of 0.7857. Look at what Excel got. There it is, adjusted 0.7857. I'll put stars by it. So my point is, as you can see, these are the 3 numbers: R squared, adjusted R squared. Let me make this wider so you can see it. And standard error are the 3 numbers we're using to determine which model's better. And now you can see how these numbers are calculated for each model before you compare them. Any questions? This is it. That was the hard part of today's lecture. Let me look at my notes. Seriously? That was it? How are we doing on time? Any questions? Okay, go ahead.
So for Intercept, when it's like, where did you get, what number did you plug in for X?
Oh, you know what I forgot to do? I apologize. That's supposed to be the mean of X. And the number I plugged in there is 4. So 4 times 1.25 minus 7, subtract from 7 equals 2. Because the mean, I forget to put the mean of X in. Good question. Any other questions? Well, is that it? We're ready for the incline? But again, I want to show you something new. I'm gonna turn this off.